Chapter 19, Lesson 4. Previously we have defined delta G and talked about how delta G tells you whether a reaction will happen on its own or not, whether it's spontaneous or not. And we said the two factors were delta H and delta S, including temperature. Temperature was the third factor that can swing delta G from one side to the other. Now we're going to give you some more equations that relate delta G to some other concepts. This equation allows us to calculate delta G at non-standard conditions. We have kind of taken for granted that the not that we've seen in our equations, this little zero, means at standard conditions, which include 25 degrees Celsius for us. It also includes 1 atmosphere, and it also includes 1 molar solutions, which it doesn't bother us too much here. But if we are not at these standard conditions, then delta G will be different, which makes sense. If you change the temperature, we understand that delta G will change. So there is a way for us to relate gaseous systems and aqueous systems to see how those systems affect delta G. So this is essentially a broadening of this idea of delta G, encompassing or putting together other concepts. Q, recall, is from the equilibrium chapters. Q is the same as K except at or before equilibrium. Q is products over reactants, our famous reaction quotient. So we can use this equation to find delta G's at other interesting situations or under interesting conditions. In fact, that's exactly what we'll do. So we said the delta G is delta G naught plus RT ln Q. Now, real quick, we don't say this here, but R is a special constant. It's the gas constant. However, the gas constant that we used for the gas is 0.08206 liters atmospheres mole Kelvin, will not be able to be used here because we have to align R with the units of G, or delta G, which is kilojoules. So we have to have the R value that uses kilojoules or joules. And in fact, that value is 8.314, if I'm not mistaken. In fact, I'm going to go down just in a second. Here, actually, it is on the next slide. We're given this value. In both cases, we must use this value. And this is joules per mole Kelvin. So we will have to consider for both of these equations. We'll go back to this equation in a minute, but this is the equation actually that we're looking at for the previous example. So let's go ahead and calculate delta G then under these non-standard conditions. First, let's go ahead and calculate delta G under standard conditions. We'll need that value. So delta G is products minus reactants. In this case, the products is NH3. Let's look up the delta G for NH3 under nitrogen. And it is negative 16.66 kilojoules. For H2, remember for H2 and for N2, because these are both elements, delta G will be 0 for this one and for this one. So effectively, delta G naught is negative 1666 times 2 multiplied by 2, which is, when you do this in your calculator, should be about 33-ish. .32 kilojoules. This is delta G under standard conditions. Let's go ahead and plug these numbers in. Q is products divided by reactants. So we are given the pressure of NH3 to be 1.4. Let's go ahead and do 1.4 squared because of this 2. Don't forget to square it, over N2, which is 2.5, and H2, which is 6.4. Don't forget to cube it. 6.4 cubed. Let's go ahead and evaluate Q now. Go ahead and do the top and then do the bottom. So 1.4 squared gets us 1.96, and the bottom 6.4 cubed times 2.5 gets us 655.36. Divide the 2. 655.36, and this value gets us 0.00299. Okay, let's go ahead and plug the rest of the values in. Temperature is 25 degrees Celsius, so T for us will be 298. Remember, 25 plus 273. We want to use absolute temperature in all calculations involving temperature. This is 298 Kelvin. This is our third value, and R has been given to us earlier as 8.314 joules per mole Kelvin. If you take a look at per mole Kelvin. Now, because we are dealing with kilojoules, we either have to get kilojoules into joules to line up with R, or get R into kilojoules to line up with delta G. So I would suggest, because our final answer we want the delta G, let's get R to align with our delta G. So in fact, R will divide by 1,000 and become 0.008314 kilojoules per mole Kelvin. So we have all our values, and all that's left to do is plug and chug, which we can easily do. So our delta G equals negative, this should be a negative number, negative 33.32 plus R is let's see, plus 0.008,314. It's going to get a bit crowded, so hang on. Plus temperature, which is 298, times the natural log of Q, which is 0.00299. 0.00299. Let's go ahead and value these. I would begin with the natural log, 299, then multiply by 298, multiply by 0.008,314, and we get negative 14.4 for this value. So we get negative 33.32 minus 14.4 for a total of negative 47.7 kilojoules. So under these conditions, delta G becomes more negative. The original delta G was 33.32. Here it becomes more negative, so it becomes more spontaneous. The conditions have changed, and in fact it depends how far away we are from equilibrium. Because we move further from equilibrium, the delta G has changed. So here's how you would calculate delta G under non-standard conditions. We're going to give you one more equation. In fact, this is pretty fantastic, but we can derive the equilibrium constant from the delta G's. This should get you excited enough to leap for joy, because this kind of shows you how interconnected and interrelated all these concepts in chemistry are. So all we do is we assume that under equilibrium conditions, if we are at equilibrium, then delta G becomes 0. We had said this earlier. So this one drops out of the equation, and then we can simply subtract the RTL and Q term to the left side. That's why it's negative now. And to get rid of ln, we first of all we divide the RT, divide by negative RT, and we divide by negative RT here. And then to get rid of ln, the inverse or the opposite of natural log, just like we rose regular log 10 to that power to get rid of it, you would raise e to the power of ln. If you know anything about natural logs, that is how you undo natural logs. And you do e, so this cancels out, and you do e to this power, and you come up with k equaling this. So take a look and marvel at this. In fact, what this is saying is, if we know delta G, if we know what the spontaneous number is, we can find out K, because the rest of these technically are constants. E is a mathematical constant. This is just for math. If you know, this is related to the compound aggregation of exponential functions. And R is a constant, and T is easily obtained. That's the absolute temperature. So this allows us to find equilibrium constants from delta G values. So that is what we can do here. So tell a friend and do an example or two. In fact, let's do that on the next slide. So we got K. The equation said that K is equal to E negative RT over, if you take a look, negative delta G over RT. Let's try that again. Negative delta G get rid of that little guy. No. Negative delta G over RT. Okay, let's go ahead and apply this concept here. And here it says, from Appendix C, go ahead and use delta G values to obtain K. And again, watch the R units. Remember we said that R for our case will be 0.008314 kilojoules per mole Kelvin. So our temperature is 25 degrees Celsius. That should be degrees Celsius. So our temperature again is 25 plus 273, which is 298 Kelvin. So we got that value. We got the R value. The delta G value we'll have to take from Appendix C. And again, let's do products minus reactants. So delta G, if we take it from Appendix C, that means we're going to be under standard conditions. So that will be that little zero. SO3, find SO3 and multiply by 2. So we get 2 times SO3, which is under sulfur, negative 370.4, and subtract from that the reactants. Remember, oxygen will have a 0 value, so don't worry about oxygen, minus 2 times SO2, which is negative 300.4. So evaluate this one step at a time to ensure accuracy. So 2 times negative 370.4 gets us negative 740.8. We're going to subtract the negative, so in the end we're going to end up adding a positive. So 2 times 300.4 should be 600.8. And adding these numbers together should get us negative 140 kilojoules. Okay, let's go ahead and plug and chug. K is equal to E. Now remember, this is your constant. E is this, and make sure you can find E on your calculator. This is the mathematical constant 2.7. So either find the E button, or if you don't have the E button, which you should, this is 2.718. It's just like pi. It's an irrational number that just keeps repeating with no set pattern. So let's do E raised to the negative. Now notice it's going to be negative delta G, so we have to take the negative of negative 140 divided by R is 0.008314 times 298. So it'll be important to evaluate this part by part. So let's go ahead and evaluate this top number. We got E raised to the power of negative. Go ahead and evaluate the bottom first. 0.008314 times 298. We got 2.477. 2.477. 0.78 if we round it. And then we've got essentially positive 140. So positive 140 divided by that number gives us 56.49. So e raised to 56.497. If you evaluate this value, you will get a very big number. We will get 3.44 times 10 to the 24th power. And this is a k value. K values can be this big. It's not unusual that k values are this huge. If your delta G value is sufficiently large, then you essentially will be raising it e to that power, and it would make sense that we'd come out with this very big number. So we're able to calculate k values from delta G values. Hopefully this was an interesting exercise, and this should conclude for us chapter 19 altogether.